What specific problem does the proposed method aim to solve in the context of reasoning ability in large language models, LLMs?
The proposed method aims to solve the problem of improving the reasoning ability of large language models, LLMs, in the context of artificial intelligence. Specifically, the method addresses the challenge of enhancing the reasoning capabilities of LLMs for complex problem-solving and advanced intelligence development. The paper discusses how existing approaches such as prompt-based methods and tool-calling methods have limitations in consistency and effectiveness, requiring additional prompt designs and high-quality textual data. To overcome these challenges, the paper introduces a novel training scheme called self-play from Adversarial Language Game, SPAG. SPAG utilizes an adversarial language game called Adversarial Taboo to enable LLMs to improve their reasoning capacities through self-play without the need for human knowledge. By engaging LLMs in an adversarial conversation where one player aims to induce the other to speak a target word unconsciously, the method provides a structured yet generalizable approach to enhancing LLM reasoning abilities. Through offline reinforcement learning on game outcomes and iterative self-play processes, SPAG demonstrates significant performance improvements on a wide range of LLM reasoning benchmarks, offering a more efficient and effective way to enhance the reasoning capabilities of LLMs.
How does the proposed method, self-play from Adversarial Language Game, SPAG, work? Please illustrate step by step.
The proposed method, self-play from Adversarial Language Game, SPAG, works in the following steps. 1. Imitation learning. Before the self-play stage, imitation learning is conducted to ensure that the LLM behaviors follow the game rules. Trajectories are collected from GPT-4 self-plays, divided into attacker-winning and defender-winning sets. 2. Reinforcement learning from self-play. The LLM plays as the attacker and defender alternatively in self-plays. An offline learning scheme is used to collect self-play episodes, update the LLM policy through reinforcement learning, and prevent overfitting. 3. Adversarial game objective. The objective of the adversarial language self-play is to maximize the total reward in the game episodes, considering both attacker and defender policies. 4. Policy gradient optimization. Policy gradients are calculated for the attacker and defender, utilizing importance sampling to estimate expectations. The learning loss is designed to optimize the objective with a KL regularizer to prevent overfitting. 5. Reward threshold selection. Episodes with positive rewards for the attacker and negative rewards for the defender are selected for training, ensuring effective learning from successful game strategies. 6. Final SPAG objective. The final objective of SPAG includes maximizing rewards from self-play episodes and maintaining general language abilities through supervised fine-tuning data. 7. Training details. Training setups include specific learning rates, KL penalty coefficients, batch sizes, and reward decay weights. Each training process maintains one epoch to iteratively improve reasoning and language capacities. 8. Result analysis. The effectiveness of SPAG is verified through reasoning benchmarks and gameplay win rates. The LLMs show steady performance improvements on reasoning benchmarks and win rate enhancements in the game against GPT-4 and each other. 9. Ablation study. An ablation study is conducted to compare the performance gains from SPAG with supervised fine-tuning data. The results show that SPAG models outperform the SFT baselines, indicating the significant contribution of the self-play and reinforcement learning scheme. 10. Overall impact. SPAG enhances LLM reasoning abilities and game-playing skills through iterative self-play, reinforcement learning, and careful optimization, leading to continuous performance improvements and advanced language model capacities.
What are the theoretical or practical benefits of using the SPAG method over traditional reasoning improving approaches for LLMs?
The theoretical and practical benefits of using the SPAG method over traditional reasoning improving approaches for LLMs lie in its ability to enhance reasoning capabilities more efficiently and effectively. The SPAG method leverages self-play in an adversarial language game setting, allowing LLMs to continuously improve their reasoning skills without the need for human annotation efforts or high-quality textual data. This approach enables LLMs to generate synthetic data internally, leading to a more cost-effective and scalable solution for enhancing reasoning abilities. Additionally, the SPAG method promotes generalization by covering a broad range of topics through the use of target words from a vast vocabulary, ensuring that LLMs can improve their reasoning capacities across various domains. Furthermore, the explicit and automatic judgment of game outcomes in SPAG simplifies the evaluation process, making it easier to assess and track the progress of LLM reasoning improvements. Overall, the SPAG method offers a novel and promising way to develop advanced LLM capacities by combining self-play in an adversarial language game with reinforcement learning, leading to significant performance enhancements in reasoning benchmarks and gameplay win rates.
How is the SPAG method validated or tested in the paper's experiments?
The SPAG method is validated and tested in the paper's experiments through a series of evaluations. Firstly, the effectiveness of SPAG is verified by selecting open-source pre-trained LLMs, Llama 2-7b and Baichuan 2-13b, and evaluating their performance on reasoning benchmarks and gameplay win rates. The reasoning benchmarks include Big Bench Hard, Arc Easy and Challenge, Mutual, Wino Grande, Logica 2, PIQA, and MMLU. The gameplay win rates are tested on a testing vocabulary containing 150 typical words. The win rates are calculated based on the number of winning episodes, losing episodes, and tied games, ensuring the improvement of ILM's game skills through reinforcement learning of self-play. Additionally, the paper conducts an ablation study to compare the performance gains on reasoning benchmarks between the SPAG method and supervised fine-tuning (SFT) models. The results show that the SPAG models outperform the SFT baselines, indicating that the major contribution to reasoning improvements comes from the self-play and reinforcement learning scheme of SPAG. Overall, the validation and testing of the SPAG method in the paper's experiments involve comprehensive evaluations on reasoning benchmarks, gameplay win rates, and comparison with SFT models to demonstrate the effectiveness and superiority of the SPAG training approach.
What results were achieved with the SPAG method in terms of reasoning benchmarks and game win rates?
The SPAG method achieved significant improvements in reasoning benchmarks and game win rates. In terms of reasoning benchmarks, both Llama 2-7b and Baichuan 2-13b showed steady performance improvements across multiple benchmarks with each epoch of SPAG training. The SPAG models surpassed the imitation learning models and even outperformed the supervised fine-tuning baselines on reasoning benchmarks. Specifically, the SPAG models demonstrated notable advancements in reasoning tasks such as Big Bench Hard, Arc E and Arc C, Mutual, Wino Grande, Logica 2, and PIQA. Additionally, the SPAG models exhibited continuous enhancement in game win rates when playing against GPT-4, showcasing improved game-playing skills through self-play reinforcement learning. The defender's performance notably improved through SPAG training, as evidenced by the increased win rates when SPAG models played against each other. Overall, the SPAG method proved to be effective in enhancing both reasoning capabilities and game-playing skills of the large language models, showcasing its potential for developing advanced language model capacities.
What are the limitations or drawbacks of the SPAG method based on the information provided in the paper?
The limitations or drawbacks of the SPAG method, as outlined in the paper, include the heavy computational complexity due to the massive multi-turn autoregressive text generation involved in the self-play sampling process. This complexity can make online reinforcement learning training inefficient. Additionally, the self-play process relies on offline learning schemes, which may not fully capture real-time interactions and dynamics that could occur in an online setting. Another limitation is the potential for training instability with negative advantage values, which can be caused by exposure bias of the autoregressive language model during the policy gradient optimization. This can lead to ineffective game strategies and hinder the improvement of the LLM's reasoning abilities. Furthermore, the SPAG method requires careful selection and preparation of training data, including target words, imitation learning data, and supervised fine-tuning data, which can be resource-intensive and time-consuming. Lastly, the SPAG method may not guarantee continuous improvement in general language understanding performance, as seen in the slight decline in performance for Baichuan 2 to 13b during SPAG training.